Hello everyone, I am Professor Anishwara and I welcome you all in this video lecture. Currently, as you know, that we are running a series of video lecture on design of synchronous machine. Currently, we have started design of Salient Pole type of rotor. In previous lectures, we have seen design for pole dimension, design for field dimension, as well as design for the field winding. In this video lecture, we'll study about design of damper winding. So let us start with function of the damper winding. First of all, the function of the damper winding should be very much clear. And we know that the function of damper winding in case of synchronous alternator or in case of synchronous motor, it is quite different. For synchronous alternator, the function of damper winding is to suppress the negative sequence field and to damp the oscillations when machine starts hunting. Same way in synchronous motor, the function of damper winding is to provide starting torque. In case of synchronous motor, we know that it is not a self-start motor. Either we can start as an induction motor or we provide damper winding. So one of the function in case of synchronous motor is to provide a starting torque. And the second function, that is to develop damping power when machine starts hunting. So if functions are clear, then position of the damper bars or damper winding should be very much clear. So we have here drawn a cut section of the Salient pole. So one of the Salient pole we have drawn here. So this is our damper bars. At the center of the pole, we have minimum air gap, and that is LG. LG is the air gap length. And when we travel towards the tip of the pole, we have slightly increased air gap length, and that is known as LG dash. We have height of the pole shoes. Height of the pole shoes in case of when we use the damper bars, it is important. So HL, that is the height of the pole shoes. Then we provide the saliency and the height, that is HG. And ultimately, diameter of the rotor bar. Here we can see the diameter and the diameter of the damper bars. So during design, we need to find out total number of damper bars, diameter of each damper bars, length of the each damper bars. So this way we can design our damper winding. So position must be clear, and what exactly we are going to design during this designing work, that should be very much clear in the mind. So let us first see the magnetomotive force distribution. Let us take Q, that is slots per pole per phase. Then we have ZS, that is a conductor per slot. IZ, that is RMS value of the current in each conductor. And AT and suffix M, that is amplitude of phase magnetomotive force. Let us take ATM, that is equal to maximum conductor current and multiplied by number of turns per pole per phase. We know that magnetomotive force, that is ampere turns, that is nothing but a product of current as well as number of turns. So here we have taken ATM is equal to maximum conductor current multiplied by number of turns per pole per phase. So if we substitute the value, then root 2 IZ, that is our maximum peak current multiplied by slots per pole per phase and multiplied by conductor per slot divided by 2. So to find out the number of turns. So again, if we substitute the values, then ATM, that is root 2 Iz multiplied by Q, that is number of slots per pole per phase, and multiplied by Zs divided by 2. Zs, we know that it is a number of conductor per slot, and divided by 2. So ultimately the equation of the ATM will be Q multiplied by Zs multiplied by Iz and divided by root 2. So this equation is very important and it must be clear. Now, design of damper winding. We are designing our damper winding to suppress the inverse rotating field. So now we have to calculate magnetomotive force for the damper winding. Now onwards we start our actual design work for the damper winding, and we should know the magnetomotive force, because the function of the damper bar or damper winding is very much clear, and it has to produce exact and equal and opposite damping power to suppress or to damp out the oscillations. So magnetomotive force for the damper winding we need to understand and we need to calculate. So we start with amplitude of the fundamental of the magnetomotive force, and let us call it AT1, and that is equal to 4 by pi multiplied by ATM and multiplied by fundamental winding factor KW1. We know the value of ATM. Suppose if we substitute the value of ATM, just we have derived values or equation for ATM, and that is Q, that is number of slots per pole per phase, multiplied by Zs and multiplied by Iz divided by root 2. Still, if we substitute values for Iz, that is I phase, and Zs, that is 2 multiplied by total number of turns per phase and divided by Q divided by P. This value we can substitute, and so our equation of ATM, now after substituting these values, it change to root 2 multiplied by I phase multiplied by T phase and divided by number of pole P. Now if we substitute this value of ATM into equation of AT1, AT1 is our fundamental magnetomotive force, then AT1 becomes 4 multiplied by root 2 divided by pi multiplied by I phase multiplied by T phase multiplied by KW1 and divided by number of pole P. Now from this equation, it is very much clear that this magnetomotive force is a pulsating magnetomotive force, and this pulsating magnetomotive force can be resolved into two parts. One part that is known as a synchronous magnetomotive force, and another part that is known as a inverse rotating magnetomotive force. Now function of damper winding is very much clear, and if we need to suppress the inverse rotating field, then damper winding must have to develop equal and opposite magnetomotive force compared to our inverse rotating field magnetomotive force generated by the fundamental pulsating type of magnetomotive force. So if we consider magnetomotive force for the damper winding, then we have to take half of the magnitude, because this pulsating magnetomotive force is equally, it can be resolved into two parts, and both the part having equal magnitude, that is half. So if we now consider magnetomotive force for the damper winding, then we can take half of the magnitude as per the 81. So that comes to 4 multiplied by root 2, now divided by 2 pi, multiplied by I phase, multiplied by T phase, and multiplied by kW1 divided by number of poles P. Equation is similar, but the magnitude now it is half compared to our 81. Now if we proceed further, then we know that ampere conductor per pole, that is AC is ampere conductor, and tau, that is our pole pitch. So ampere conductor per pole can be given as a 6 I phase, T phase, and divided by P. P is number of pole. This equation is very much known and we have derived in at very initial stage. So from this equation we can say that I phase, T phase, and divided by P, that is equal to product of AC, tau, and divided by 6. Now we have to substitute this value in our magnetomotive force equation of damper winding. So if we substitute this value, then magnetomotive force for the damper winding, that becomes 4 multiplied by root 2 divided by 2 pi multiplied by AC, tau, multiplied by kW1 and divided by 6. So if we simplify further, then our equation becomes 2 multiplied by root 2 divided by pi multiplied by AC, tau, divided by 6, and multiplied by, if we substitute the value of kW1, that is our winding factor, with 0.955, and then ultimately if we simplify further, then it becomes 0.143 multiplied by AC, that is our ampere conductor, and multiplied by tau. Tau is a pole pitch. So magnetomotive force for the damper winding we have calculated. So our first step is over. The first step is very critical to calculate exact magnetomotive force to be generated by the damper bar, and the function of the damper bar, as we have discussed, that the function of the damper bar is to suppress the inverse rotating field. So how much magnetomotive force to be generated by the damper bar, that is very important. So ultimately we have calculated this through the equation, that is 0.143 times AC tau. So now the remaining design is very simple, and based on this magnetomotive force to be generated by the damper bar or damper winding, we can do the further designing. So now area of the damper bar, let us consider capital A and suffix D. A is for the area and D is for the damper bar. So AD, that is total area of the damper bar per pole, and delta D, that is current density in the damper bar. Suppose we take the product of AD and delta D, that is total area of the damper bar and current density, then it can be exactly equal to the magnetomotive force to be generated by the damper bar, and that we know, or we have rather calculated, that it is a 0.143 multiplied by AC and multiplied by tau. So from this equation it is very simple to calculate total area of the damper bar per pole, and that becomes 0.143 multiplied by AC multiplied by tau and divided by delta D. In actual practice, we provide slightly greater area of damper bar compared to calculated one. So 0.143 times AC multiplied by tau divided by delta D, that is our calculated value or rather estimated value. So in actual practice we provide slightly greater area, so that is 0.2. 0.2 normally as a standard we take. So it is 0.2 multiplied by AC multiplied by tau and divided by delta D. Current density normally we can take in damper bar also, that is 3 to 4 ampere per millimeter square. So this way, after calculating magnetomotive force to be generated by the damper bar, based on that magnetomotive force, we are able to calculate total area of the damper bar after assuming suitable value of the current density through the damper bar. So now next step, that is to calculate the length of the damper bar. The length of each damper bar can be considered as L, that is length, and suffix D, that is for the damper bar. So LD, that is equal to, it can be equal to 1.1 times L. L, that is a stator core length, and for smaller machine, directly this equation can be utilized to calculate length of the damper bar. So that is a 1.1 multiplied by L. And for a larger machine, length of the damper bar can be calculated as L plus 0.1 meter. Slightly more or slightly greater length is to be provided because all the damper bars, ultimately we have to short circuit with a short circuiting ring. So damper bars, length of the damper bars are slightly more compared to our stator core length. So after calculating length of the damper bar, the next step, that is a number of damper bars. So we just draw for our reference, and we can easily understand from this figure how to calculate number of damper bars. Total area of damper bar, as we have calculated from the magnetomotive force equation, total area of the damper bar. So total area of damper winding is distributed into smaller cross section depending upon the number of damper bars. So basically it depends on the pole arc, available area in the pole arc. So it can be considered as a pole arc is equal to number of damper bars per pole multiplied by slot pitch of the stator and multiplied by 0.8. Now it is very important to understand here that in case of damper winding, the damper slot pitch is considered as exactly equal to the stator slot pitch. So gamma S, as shown in this figure, that is a stator slot pitch. So in case of damper winding also, the damper bar slot pitch we can consider as exactly equal to the stator slot pitch. But for practical purpose, to reduce the current induced in the damper bar because of tooth ripples, we take 20% higher or 20% less slot pitch for the damper bar compared to stator slot pitch. So here we have taken 80% of the stator slot pitch. So our pole arc is equal to number of bars per pole multiplied by slot pitch of the stator and multiplied by 0.8. So from this equation, pole arc is known, and ultimately we can calculate ND. ND is the number of damper bars multiplied by gamma S and multiplied by 0.8. So all the quantities are known, and from this equation it can be easily calculated number of damper bars, how many number of damper bars can be accommodated in our available space in the pole shoes, and that depends on the pole arc. So our total area of damper winding, now it is distributed into smaller cross section, and that depends on the number of damper bars. Now we have to find cross section of the damper bars. Total area is known. Now total number of damper bars to be used, that is also known. So now cross section of the damper bar. So cross section of each damper bars is very simple. So total area of bar per pole and divided by number of damper bars per pole. So equally distributed in each total number of damper bars we use. So AD, now small a, that is for the cross section area, and D is for damper bar. So for each individual damper bar we have area of cross section, that is AD divided by ND. AD is a total area of bar per pole, and ND, that is number of damper bars per pole. So from this equation we can easily able to calculate total cross section area of each damper bar. And suppose we use circular bars, and in most of the cases we do, then AD, that is area of a damper bar, that is equal to pi by 4 multiplied by DD square, where DD, that is a diameter of the damper bar. So from this equation, area of each damper bar can be calculated, and from the area, diameter of each individual damper bar can be easily calculated. So in damper winding design, as I said earlier, that we require length of the damper bar, number of damper bars to be used, total area of the damper winding, and total area of each individual damper bar, and ultimately diameter of the each individual damper bar. So this way we can complete our design for damper winding, and at last, as I said, that all the damper bars are short circuited with the ring. So area of each ring short circuiting the bar, and area of ring, a ring, that can be considered as a 0.8 or equal to area of total area of the damper bar. So this way we can complete our design of damper winding for salient pole type of synchronous rotor. So I must stop here. Thank you for watching my video. Keep watching. Thank you very much.